Yeah. So they're very hard because of strong interatomic metallic bonds. And this interatomic metallic bonds depends on the availability of free electrons. So in the case of D, this thing, you get electrons from S as well as D orbital. So more number of electrons means stronger bonds. And based on this, because of this, we can see that the exception to this would be, again, zinc, cadmium, and mercury. In fact, mercury is like so exceptional that it is the only liquid metal at room temperature. Okay. Because in this case, all the d electrons are paired up, which means it has very like only the s electrons available for this interatomic metallic bonding. So lower number of electrons means the bonds are relatively weaker. And this in turn affects the trend of melting point. So in general, D block elements have high melting point. What do you think would be the trend within a period? Like if you look at the 3D series, what do you think would be the trend of the melting point?
As in like down the group?
Across a period.
Increasing.
Oh. Yeah, increasing.
Continuously?
I don't know, there might be some anomalies, but
changes. Yeah, for a transition, there might be.
It increases up to manganese and then decreases again. Like this is specific to 3D series. Like the topmost.
Which element is after manganese?
Manganese is 25, so 26, chromium is 24, iron. Manganese ke baad iron.
This is only for the third period and after like fourth and all.
Fourth, fifth also. Like I need to look up the metals that are below manganese. But yeah, the general trend is that it basically like melting point increases up to D5 configuration and then uske baad it decreases.
Is there a reason for that?
Yeah. Reason is related to its hardness. Like abhi discussed kiya. So more is the number of electrons, like free electrons available for roaming around, the stronger will be the bond, right? They're all held together by that sea of free electrons. So D1 may you have like 4s2, so that's constant. And then you have D1, D2, D3, D4, D5. I mean, D4 doesn't exist, but yeah, D5. Like these are the number of electrons is increasing up to D5. So the interatomic metallic bonds also increases up to D5. D6
so is the hardest metal in its period?
in its period, yes. Okay. So
wait, so manganese is only for one period, like right? So what about the others?
yeah, that's what I'm just like looking up which one it is. Manganese ke baad 4D in the case of 4D, it's technetium. TC is the middle one with D5 configuration.
So do we have to remember that?
Yeah. Yeah, if they're asking about trends as a general thing, it increases up to D5 configuration and it decreases. 3D में D5 is manganese and 4D में D5 is technetium. And next one, the highest is like 5D series में tungsten. W is the highest one. After tungsten, it starts falling.
Why doesn't D4 exist?
D4
Oh, because one will shift. Yeah. Okay.
interesting है. Now D5 के बाद for D6 pairing starts.
What? Sorry, why D4 doesn't exist?
Chromium में क्या होगा? Like 24 supposed to be D4, no? What happens in chromium?
Oh, yeah, actually. Acha.
Yeah.
Wait, so that means it doesn't exist only. Oh.
I mean, the higher elements it's not like it's zero. Chromium के case
Yeah.
में it doesn't
Yeah,
exist.
like for some elements, like chromium is not that many electrons, but like more further down the periodic table, it still won't exist.
Like you will only have 3 cases of D4 theoretically. You have chromium, उसके नीचे वाला element और उसके नीचे वाला element.
तो सबसे नीचे वाले में हो सकता है.
हाँ, 6D में you find it.
Yeah.
5D में again because you have 4s also filling up, you find D4F something that way there.
So even in 5D वाले में it will shift, na, for like 5D.
3D and 4D it shifts. Once the F orbitals also start filling up, the irregularities also become a lot more. So like I'm looking at the electronic configuration. So 6s 5D and 7s 6D में I can see there's D4 existing. D1, D2, D3, D4 भी है. At 7s में you have 7s2 and then 6D4 because there the F orbital, the number of electrons, like there it shifts up, I guess. Once the F orbitals comes into picture, things get really complicated. Like a lot is not known about F orbitals ka situation. Yeah. Trend in boiling point, yeah. It increases up to a point and decreases. Highest melting point in each series, you have manganese in 3D, technetium in 4D, and tungsten in 5D. Okay. And the reason is, yeah, the number of actually, sorry, my bad. It increases up to just before manganese. Like these two are exceptions here. So up to before manganese, and then after manganese, they start falling.
So manganese has, yeah.
Okay. So in this case, yeah, chromium has the highest, and then it starts falling from manganese onwards. The general thing, like noted down as increases up to D5 and decreases. Highest boiling point just needs to change, like just go one before manganese. So in the case of 3D series, highest is chromium. 4D may what comes before technetium? Table, molybdenum. And 5D series may it is tungsten. So these are the highest. The concept remains the same. Like more number of unpaired electrons means stronger bonds, which is what in turn affects the melting point. Stronger bonds means it takes more energy to melt it out. Once pairing starts, the number of unpaired electrons, which means the number of electrons available for like freely roaming around, that starts decreasing, and that's why that causes the decrease afterwards. Now, these two are like manganese and technetium are exceptions because D5 is stable. These electrons will not want to get out of their stable configuration. They'll just like be in their D5 configuration. So that is the reason there's like a special case. This is an anomaly which has like lower thing. Otherwise, yeah, it increases up to a point and decreases. Manganese technetium has lower than expected melting point because of the stable D5 configuration.
So it starts decreasing from magnesium, technetium, and whatever it is, and the tungsten, right?
No, tungsten is the highest. So the one after tungsten जो भी है, rhenium से it starts decreasing.
Matlab for 3D and 4D, it decreases from magnesium and tungsten,
Manganese.
manganese and
Technetium. TC
Yeah,
telling is TE.
that's fine. But in case of 5D wale mein, W is highest and then it start decreasing. Vaisa. Okay, and what? So that's what you've written. Cr like chromium, molybdenum, and tungsten, right? Highest.
Yeah.
Tungsten is W.
Tungsten is W, yeah. Same reason why potassium is K and sodium is Na.
And tin.
Tin is Sn. Yeah.
There are so many: gold, silver,
Iron,
mercury,
mercury.
mercury also.
Okay, so that's high melting point. Yeah. Metallic bonding. In a row, it increases to D5. And so these two specifically have like lower, so it goes and then dips and then it decreases. Is our graph. And the reason is that D5 stable configuration, the electrons like once they're stable, it's difficult to like get them out. Same reason why noble gases don't react.
What is MO?
MO is molybdenum. This is chromium, molybdenum, tungsten.
How is D5 wale, being stable reasoning for manganese to have lower than normal melting point?
So D5 is stable electronic configuration, right? So it's difficult to remove electrons from a stable electronic configuration. That's why you have those anomalies with ionization enthalpy. Remember, like nitrogen is like, it has a higher, like you can't get the electron out because half filled and fully filled are more stable.
But MN
Oh, okay.
Yeah, Kaveri, you
But
got
how does it make it lower?
so
How does it reduce the melting point?
lower number of electrons available in this electron sea, weaker metallic bond. So it's easier to melt it into a liquid. Lower amount of energy taken to break them apart.
But stable,
More
hoga, so
stable
means
more energy
That's
required. So
chemically
more.
stable chemically. You're spending this energy not to get the electrons out. You're spending the energy to melt melt the block of metal. Like just
Oh,
separate out.
stability is chemical and melting is
Yeah.
physical.
physical, yeah.
But still in their periods, MN and TC are the highest, right?
No, they're like lower. Are they? No, I don't think they're the lowest, but there's a dip there. These are the
But
highest.
it increases up to D5, right?
Yeah, so even
it
though they are
increase-
lower than the like chromium, molybdenum, and tungsten, they should be highest in their period, right?
They won't be the highest. These are the highest. They are like, see, the graph kind of looks like this. So it's not like this. It's like it increases up to a point. There's a small dip and then it reduces. So why is that dip? That's that manganese, and this is like specific only to manganese and technetium. So you observe this dip only in the case of manganese and technetium. That's why we mention them specifically.
Ma'am, but you had said that across a period it increases up to manganese and then decreases. So that
Yeah,
means
so
manganese should be
no, that's why I
highest in that.
corrected it after that. I realized my mistake. Like up to matlab before manganese. So chromium is the highest, and from that there's that dip. Because of
But
because
D5 is manganese, right? So up to D5 means up to manganese it increases. So like it's the
technically that
same
should
thing.
be the case, but because of half filled, like chromium also has D5 but S1. इसमें D5 and S2 stable electronic configuration. That's why there's a dip at manganese. Yeah, that's why I asked you guys to correct it. Like, इसलिए I've like corrected it and mentioned it separately. Yeah, highest is not manganese. These are like the anomalies because of stable electronic configuration. So it's difficult to get those electrons out for this.
Yes, you said that thermal conductivity, like you said, electrical conductivity, thermal conductivity, and then excess of electrons. How is thermal conductivity related to electrons?
How much, like, okay, how much do you guys know about conduction? Solids may, how conduction happens, what happens there and all.
Like in terms of electrical, I think I know that, but I
And
don't know how.
conductivity.
Thermal, oh, I know like latent heat and specific heat capacity and all.
No, not the terms, the process conduction कैसे होता है.
Yeah, I mean,
Actually, I can
kind of.
explain it very simply. So conduction is when heat passes through the solid. Like suppose you have a solid bar, and if I start heating this end of it, eventually if it's a
Yeah.
conductor, this end also should have a higher
Will, yeah,
what actually happens is, again, heat is how fast the particles are moving, right?
yeah,
If I apply heat on this end, these particles are going to be vibrating really, really fast.
yeah,
As yeah, they are vibrating really fast. When they hit the particles adjacent to them, molecules, atoms, jo bhi hai, they will transfer some amount of energy, and these will start traveling fast.
yeah,
And then that keeps going on and on and on.
yeah,
For metals may, because you have free electrons, they're free to travel in between it. So it's not restricted to going one at a time. So as the electrons travel, they can carry that higher energy with them and then make these particles also vibrate really fast. Particles vibrate
yeah,
really fast, matlab higher temperature.
yeah.
So easier that the particles can travel, higher or better is the
But the particles are not traveling. Only the heat is being, like energy is being transferred from.
electrons are traveling, no? Like motion of
But why electrons will travel?
Electrons travel, they will only transfer the heat energy, right?
Yeah, they'll only give the energy to the next set of.
they are more mobile than
molecules.
the individual atoms that are present here, right?
But that doesn't mean that the electrons, like present in the orbits will move in.
No,
If you're providing
of
heat,
electrons, like electrons are mobile. They are more mobile than the individual atoms that are there. That's how current also happens, right? Like it's flow of electrons.
yeah. But usme you have electrical, like you have a circuit across it, right, for the electrons to travel. But here you're only providing heat. So how will the electrons? So like you're saying, the heat will provide the energy for the electrons to move.
Yeah.
But is it that the
kinetic energy?
is it the electrons moving that will transfer the heat energy, or what is it? Like, is the heat energy being transferred because of the moving electrons? Or
Yes.
how do electrons carry heat?
Heat is what? Heat is nothing but kinetic energy of the particles.
Oh, okay.
So अगर electrons का kinetic energy ज़्यादा है, when they
Yeah.
hit the things in their wave, they hit other atoms, other electrons, they will transfer.
Oh, so is that why if you have a good conductor of electricity, you have a good conductor of heat as well, because they both have the same factor, which is free electrons.
They're related.
Oh. Thank you.
Okay. Higher melting point. Huh. So the other property we discussed was they have high enthalpy of atomization. Do you guys remember the definition of atomization and enthalpy, energy of atomization?
Oh, E is ionization enthalpy.
Atomization.
Atom. Oh, I thought it was electron affinity.
Okay, let's denote it by delta HA. Enthalpy of atomization. What is enthalpy of atomization? Like, even if you don't remember word for word, see if you can deduce it. Like, naam mein hi hai, atomization.
Enthalpy of formation of atoms.
Correct. So, in the case of a metal, which is made up of atoms only exclusively, they're in solid state.
When we say enthalpy, doesn't it usually mean like breaking something up?
Yeah. No, enthalpy is just the energy change.
Yeah, so the energy released when whatever, like the electron.
No, it can be absorbed or released. That you can decide based on the numerical value. Agar positive hai ya negative hai, based on that. But it just refers to the energy. Okay, so enthalpy of atomization, as she said, like breaking it up into individual atoms. So essentially, all the atoms are held together by metallic bond. If you want to atomize them, you're breaking these bonds and then making them into individual atoms. That's what enthalpy of atomization is. So this basically, like when we talk about enthalpy of atomization for elemental metals, we are basically talking about their boiling points. Because when you make it atomic, essentially you're converting it into gaseous form where the element exists as individual atoms. Okay. So based on this, can you tell me what could be the trend of enthalpy of atomization in D block? So here also principle is the same. You're breaking this interatomic metallic bonding. तो ट्रेंड क्या होगा उसमें?
Increases.
On what basis are
Is
you?
it the same like melting point?
Yeah. So in general, D block has high enthalpy of atomization in the periodic table. And within D block, yeah, same as boiling point where it increases up to a point and then it decreases. So it increases with the number of unpaired electrons, similar to what you had with the boiling points. Okay, and very similar to your melting points also, there is a dip with manganese and technetium. Increases and then there's a dip and then it decreases.
Why is enthalpy of atomization measured using boiling point?
It's not measured using boiling point. I just See, atomization is conversion to atoms, right? When it's a covalent bond like oxygen, hydrogen, chlorine, you're literally breaking that covalent bond between them. Like they're already gases made of molecules, you're converting them into gases made of atoms. That's why it's very different from your regular melting point, boiling point when it comes to covalent compounds. But in the case of metals, because they're already made up of individual atoms only, if you're separating out these atoms, like which is what happens in atomization, the process is same as boiling that metal, like converting it, like first it's all together and then you're converting into a gas, like separating out the individual particles, right? So that's why I compared it to boiling point, to show you guys why the trend is very similar to what we had in melting point. So even though the physics, like the property we're talking about is called enthalpy of atomization, like the logic behind it, if you look at the process behind it, it is very similar to what we had. In fact, it's the exact same as what we had with melting point. Okay, so the terminology that we use is just different. That's it. Okay. So once you're done with this, then we look at atomic size and ionic size.
So this can be used for both enthalpy and for boiling point, same trend.
Yeah. We don't talk about boiling points for metals because it's extremely high. Like melting point itself is pretty high. So uske upar, if you want to boil it, you have to spend a lot of energy. So that's why you talk about it in terms of enthalpy of atomization.
Why would you want to calculate how much energy is required to make an atom of that particular element?
So thermodynamic calculations. Do you guys
No,
remember?
but don't we say that
Not make the atom, like atoms will make up the whatever it is, no? You said make up the atom. You can't make up the atom. That's not atomization. The
Atoms
atom.
are the ones making up stuff.
okay, sorry. Yeah, anyways, thermodynamic.
Do you guys remember thermodynamics may you have to calculate lattice energy of NaCl? For that,
That
we did
was,
use Hess
did
law.
we have that? I don't remember. But
We
yeah,
didn't have
maybe.
to calculate it. We just had to like explain the lattice structure of any.
No, but you had that calculation with Hess law, right? Like pehle ionization hoga, there is sublimation, then ionization, then like chlorine ke case mein the electron affinity, then enthalpy of you had
Wait,
all
Hess
that.
law is the one which says it will be equal, like it will be same either ways, right?
Yeah.
Yeah, we didn't have
Kaveri,
any.
what are you saying?
Yeah, exactly. What are you saying?
अरे Hess law is that कि कैसे भी करके हमने किया, energy will be the like enthalpy will remain the same.
This one, like if you're converting A to B, whether you do directly in one step or whether you pehle convert it to C, then D, then this way, the overall, like the energy change that you get in this one step will be equal to the energy change that you will get by adding all these steps. याद नहीं है?
Yeah, thoda sa aaya.
Yeah.
So those sort of calculations, like if you had to calculate like the most common thing that you would be familiar with is lattice energy of NaCl. Usme, if you need to find lattice energy of NaCl, you'll have the energy of formation, and then you can divide it into multiple steps. Pehle atomize sodium, then atomize karke uska ionization. Same thing with chlorine, and then Na plus and Cl minus combining, like all that. So those sort of calculations, that's why you will need enthalpy of atomization. Okay. Okay, So if you're done with this, okay, there's 2 minutes left. Atomic size and ionic size. What do you think happens to atomic ionic? Let's talk about atomic size first. What is the trend in atomic size as you go left to right across a period? Group, though, obviously it's going to increase, but there's a point to it which we'll discuss later. Across a period, what happens to the atomic size?
Increases.
Yeah. Across a period, it decreases. The special thing about D block elements or the D block series is that it is not a steep decrease between the elements. Like if you compare the first 2 periods, like the difference between the S block elements ka change and P block elements ka change, D block elements still show the same trend, but it's not as steep. Like it's fairly more comparable than S and P block.
Also, ma'am, why are we only doing for across a period? What about down a group?
We'll do that also. One thing at a time.
Oh.
Okay.
Ma'am, can you go to the previous slide 1 second?
Can you show the next slide?
So another special thing that you will find, like similar to what we saw with like noble gases and all that, is it decreases, then there's a slight increase towards the end. Now this increase is like as you keep adding